T. And now we have Q is not equal to 0. Does Q change along the length of the reactor?
Temperature inside the reactor.
Which it will.
Yeah.
Yes. Why? Because this is changing along the length of the reactor. What about TA? Does TA change along the length of the reactor? It can. There are conditions, so we did put up some of this a long time ago. If I have a cooling fluid that's absorbing this heat, and the mass is really, really, really high, or the mass flow rate of that cooling fluid is really, really high, then the temperature of that fluid might not change very much, but it's still removing heat from the system. But in general, this can also change. So both TA and T can change along the length of the reactor, and therefore Q can also change along the length of the reactor. So if we start with the integral form of, oh, don't like these things. There we go. Let's start with not that. So again, we can write out our design equation, dx dv which is a function of both conversion and temperature. And now we have another equation that we have to worry about, dt dv, which is another function of both conversion and temperature. And so if we write out our energy balance that we had previously, so this is Q into the system. So heat transfer into the system. This is shaft work done by the system. This is flow rate out. This is flow rate in. Or excuse me, I had that backwards. This is flow rate in. This is flow rate out. All that's equal to 0. And now we can take the derivative of this. Yeah.
Should the FIHI be positive?
Yeah, sorry. Yeah, flow rate in should be positive, flow rate out, negative. So this is what we would use for a CSTR. But for a tubular reactor, whether it's a PBR or a PFR, we need to use a differential form of this same equation. So dq dv, because again, now it's changing along the length of the reactor, minus change in shaft work along the length of the reactor, which for a tubular reactor, what are we going to do with shaft work? We're going to neglect it. So what's changing here is the flow rate is changing. So, are either of these changing along the length of the reactor? No. Let's go over here. How do we write this? Can either of those change along the length of the reactor? Yes. So we're going to write it this way as two summations. The first, we're going to take the derivative of the flow. And that is still equal to 0. Everybody?
Where did you get the dt dv equal to g as a function of x and t? Where did that?
That's not, I mean, that's just saying that the temperature is changing with volume as a function of conversion and temperature. It's not like a you can't use it.
Okay.
I mean, I did it up here too, right? dx dv is a function of x and t. So we just need two functions in terms of x and t. But now, for a tubular reactor, before we had this, but it wasn't a differential function, right? It was just t is equal to some function of x and t. But now it's differential. Okay, so heat transfer into the system, I can write as UA times TA minus T. Same thing that we just did, right? The change in the enthalpy of the stream with temperature, with volume, I can write as the change in the enthalpy with temperature times the change with temperature of temperature for volume. What is that? Heat capacity, right? So there's your thermodynamics review for the day. And so I can plug those in. Am I missing one? Yeah, I'm missing one. And then, what is the change in flow rate of an individual species with volume? What's the definition of that? Or what is that a definition of? It's related to conversion. Somebody say rate?
Like minus RA.
It's just rate. That's it. And of course, I can write that as the stoichiometric coefficient of that species times negative RA, which is often what we want to do. So that second part only works if we have a single reaction. But that's often what we have, right? Is a single reaction. So I can come back to my energy balance, and I'm going to substitute in those three differentials. And so what I get is U times A, TA minus T, so that's the stoichiometric coefficients times the rate, and then what else was left in that term was the enthalpies. And then we had flows times the heat capacity, dT dV, which we got from here. Because we had flow times dH dV. And again, we're neglecting the shaft work. So now we can rearrange. And what else do we know? What is this equal to?
Change nature reaction.
And so we can rearrange this. dT dV is equal to U times the heat transfer area, TA, which is your cooling fluid, or you can think of it as the room, so A as atmosphere, if you're just considering now the heat lost to the atmosphere, plus negative delta H reaction negative RA divided by so we've left it now in terms of all the flow rates, right? This isn't in terms of just one flow rate yet, but we can do that. So for a CSTR, what's different, right? Again, we have a similar procedure: Q, shaft work, inlet flow rates, outlet flow rates, this goes away. We often neglect that, not quite always. And then we can rewrite this as we're going to rewrite this part as the initial flow rate plus stoichiometric coefficient FA naught X. That's the outlet flow rate.